Today we're going to be talking about complex numbers. So, a complex number is a number that contains both a real part and an imaginary part. So I could define a complex number A, and I'm going to denote that it is a complex number by putting this bar over the letter A and say that it has some real part, which I'll call alpha, plus some imaginary part, J beta. So alpha is defined as the real part of complex number A, and beta is defined as the imaginary part of complex number A. Now, one thing to point out, because we're electrical engineering students, J may not be familiar to you. But we are going to define it to be the square root of -1. So it's fulfilling the role of I from your math courses. We can't use I in electrical engineering because that's how we define currents, and that would just be too confusing. So from here on out, we're going to use J as the imaginary operator, meaning the square root of -1. So if we plotted this rectangular complex number on a complex plane like we have shown in the middle of the board here, we would go out alpha units in the real direction and up beta units in the imaginary direction. And so we might have something that looks like this, where the projection onto the real axis is alpha, and the projection onto the imaginary axis is beta. And this would be our complex number A. We can use trig identities and come up with an exponential and polar form of this same representation. Because this complex number A has some magnitude, where I'm using the absolute value signs around the complex number A to denote magnitude, and it also forms some angle, which I'm going to call theta A, with the positive real axis. So in exponential form, A could be written as the magnitude of A, e to the j theta A. And the polar form is just a simplified shorthand notation for this. So A would be the magnitude of A, angle theta A. So these two forms, the exponential form and the polar form, are really the exact same information, just presented in a slightly different way. Typically speaking, electrical engineers will be largely working in this polar form, but we will be using an exponential form on some occasions. So these two complex numbers, the rectangular form and the exponential and polar form, are identical. They are providing the exact same amount of information, just in different ways. So it might be useful if we were able to convert between the two. So let's talk about how we could take a rectangular number and convert it to exponential first. We have a right triangle here, where the hypotenuse of this right triangle is the magnitude of A. So using the Pythagorean theorem, we can easily see that the magnitude of A is simply the square root of alpha squared plus beta squared. So that's giving us our magnitude in terms of our rectangular coefficients. And we could also figure out, using a trig identity, that theta A is simply the inverse tangent of the imaginary part, beta, divided by the real part, alpha. So this lets us convert from rectangular to exponential or polar. We can convert from exponential or polar to rectangular using these relationships. Alpha, again, is the projection of the complex number A onto the real axis. So that would be the magnitude of A cosine angle theta A. And beta is the projection of our complex number A onto our imaginary axis. So we would have the magnitude of A sine angle theta A. So now we've established ways by which to convert from rectangular to exponential or polar, and from exponential or polar to rectangular. The next topic that I would like to introduce is the concept of the complex conjugate. Okay? So the complex conjugate is denoted by an asterisk symbol, like so. The complex conjugate of complex number A in rectangular form is alpha minus j beta. So our conjugate operation is changing the sign on the imaginary portion. So in this particular example, here's negative beta. So this would be A conjugate. The projection onto the y-axis, or excuse me, the imaginary axis is negative beta. The projection onto the real axis remains positive alpha. We can see pretty easily that this is just, our complex conjugate is just our original flipped over the real axis. So we would have an angle here that is simply negative theta A. So our complex conjugate operation in exponential or polar form becomes the magnitude of A e to the minus j theta A, or in polar form, we would have magnitude of A angle negative theta A. So the complex conjugate operation simply involves changing the sign on the angle if you are in exponential or polar form, or changing the sign on the imaginary part if you are in rectangular form. So hopefully this has well defined the concept of complex numbers and the different forms that they can take. Now let's walk through some mathematical operations. So I'm going to define a complex number x, and it will have a real part, lowercase a, and an imaginary part, lowercase b. And I'm going to have a complex number y, and it will be c plus jd. So our first operation that we're going to talk about is addition. I don't know that I'm going to need this. So to add two complex numbers together, so let's define a complex number z as complex number x plus complex number y. Substituting in what we would have a plus jb plus c plus jd. We're going to add the real parts together so that we'll have a plus c plus j, and now we add the imaginary parts together, b plus d. So this is how we perform the mathematical operation of addition using complex numbers. The real parts add together, the imaginary parts add together, giving us a complex number of a rectangular form. Subtraction is extraordinarily similar. Let's define complex number W as x minus y. So this would be a plus jb minus c plus jd. This would yield a minus c plus j b minus d. So in subtraction, it's really the same thing as addition, except we have a negative sign that gets carried out into the second complex number there. So this is a plus jb plus negative c minus jd, and that's where these negative signs come from. So we just take the difference of the real part, take the difference of the imaginary part, and again, we are left with a number in rectangular form. Multiplication is a little bit more difficult. Let's define a complex number v as the product of x and y. Now, there will be times when you'll see something, this is a quick aside, where you might see x, y. This asterisk right here is not denoting multiplication. This is denoting that you are performing the conjugate operation on x and then multiplying the conjugate of x times y. So the asterisk symbol is always meaning conjugate. It is never meaning multiplication. I just want to be clear about that because it's a point of confusion among a lot of students. All right, so x multiplied by y gives us a plus jb times c plus jd. So that would be a times c plus j a times d plus j b times c plus j squared b times d. Now j squared is the square root of -1 squared, giving us -1. So what we'll find is that we will have AC minus BD, where this minus sign is coming from us adding j squared multiplied by BD, plus j AD plus BC. So again, it's not wildly difficult by any stretch of the imagination, but there is a little bit of nuance that comes in because we have this j squared term. Division is going to seem a bit awkward. Division in rectangular form. So let's say that we have u is complex number x divided by complex number y. We are going to carry out this operation by doing something that doesn't seem intuitively obvious. What I'm going to do is I'm going to multiply y conjugate divided by y conjugate. So this is just a factor of 1, but it's a factor of 1 expressed in a very specific way. And the reason that I'm doing this, and we'll find it out shortly, is that when I multiply a complex number times its conjugate, I'm only going to get a purely real result. So I'm no longer going to have a complex number in my denominator, I'm just going to have a real number. So in this case, our operations would give us a plus jb multiplied by the complex conjugate of y, so that would be c minus jd, where this minus sign comes from the conjugate operation, multiplied by C plus JD times C minus JD. So this is going to give me A times C minus JAD plus JBC minus J squared BD. I'm going to have C squared minus JCD plus JCD, so these two terms are going to cancel each other out, minus J squared D squared. And this will reduce to AC plus BD, because negative times -1 is positive, plus J BC minus AD divided by C squared plus D squared. So exactly what I said earlier, our denominator no longer has an imaginary part. It is a purely real number. So we could take the real part divided by the denominator plus J, the imaginary part, divided by the denominator, and we would again have a rectangular number as the output of our rectangular division operation. So this multiplication process was maybe slightly more difficult than the addition and subtraction operations. The division process is significantly more difficult than anything that we have seen here. What we'll find is that it's actually much easier to do multiplication and division using the exponential form of a complex number. So I'm going to define now a complex number x as the magnitude of x e to the j theta x, and a polar form complex number y, where we have the magnitude of y e to the j theta y. Our multiplication operation where we defined, let's see, v as x multiplied by y becomes the magnitude of x e to the j theta x multiplied by the magnitude of y e to the j theta y gives me the magnitude of x multiplied by the magnitude of y. And then when I multiply these two exponential functions together, I simply add their arguments. So I'll have e to the j theta x plus theta y. So this mathematical operations where I multiply the magnitudes and add the angles, in my mind, is much more easy than doing this FOIL out method. Division where I have u is equal to x divided by y. It's going to give me the magnitude of x e to the j, excuse me, there's no negative sign there, e to the j theta x divided by the magnitude of y e to the j theta y becomes the magnitude of x divided by the magnitude of y e to the j theta x minus theta y, because dividing by e to the j theta y is the same as multiplying by e to the negative j theta y. So that's why it follows the multiplication principle so easily. So our division operation is much, much more simple in our exponential form as well. If we wanted to flesh these things out in polar form, this is going to be magnitude of x, magnitude of y, angle theta x plus theta y. And this guy is going to become magnitude of x divided by the magnitude of y, angle theta x minus theta y. Alrighty, so that is all of the complex number and the mathematical operations that you are expected to be able to do in our circuit theory course. We will be dealing with a few other identities like Euler's identities and things like that in very specific instances, but we'll introduce those when we need to. Thanks for watching.